Okay, folks. So, Wednesday. Obviously, no class. So, we gotta make this video. Working on radical reactions. Looking at our radical reactions. So, we'll finish up this. Since there's no class, there's no lab. If we have class on Thursday, if school is not canceled on Thursday, if you can make it to my Thursday 1 to 3 lab, please come. We'll try to continue with the lab. If not, we'll just have to push all of our labs back by a week. We'll see how things go. I don't know. It's totally screwed things up, but we'll continue where we left off, and then Friday, one way or another, we'll probably end up looking at the homework for the chapter 13. Okay, let's get started. So, factors affecting halogenation. So, we talked about how radicals usually come from formation of a chlorine or bromine radical, which can be generated by heat, by light, or some sort of peroxide initiator. So, halogenation will then go on to attack the hydrogens of the carbons. But there are many different types of hydrogens on carbon. So what controls where the chlorine reacts? And so that's what we're talking about here. So halogenation is affected by two competing factors: the number of hydrogens available. So in some part, it's a probability game. If there's 3 hydrogens here versus 2 hydrogens here, it's 3 times as more likely to run into a hydrogen on this species. And 3 times more likely to bump into this than 2 versus 2 of that. So it's a 1.5 times more likely. But there's also a competing factor of bond strength. So just because it bumps into it does not necessarily mean all of the collisions have enough energy to tear off a hydrogen. That's why these chlorine and bromine radicals do not react with many of our functional species, because those guys have too strong of a hydrogen bond, too strong of a grip on their electrons. So remember, we talked about in radical stability, we had tertiary radicals being more stable than secondary, being more stable than primary, being more stable than like a methyl radical. So while secondary hydrogens have a weaker bond than primary, there are 3 hydrogens in a primary carbon and only 2 in a secondary carbon. So we have 2 competing things. In the case of chlorination of propane, based on the bond strength argument, we should form 2-chloropropane as the major product. However, based on the argument for the number of hydrogens, we should get a 3-to-1 ratio. So let's look at that. I'm going to quickly hop to chloropropanes so we can see that. So, looking at this, chloropropane. So, looking at that, we have 2 hydrogens here, but we have, it's not 3 hydrogens, but 6 hydrogens because of symmetry. So if we have a chlorine species, the argument, if we just go on strength alone, it should only have this molecule. Like wedge dash, it doesn't really matter wedge or dash, because symmetry destroys our chirality based on the number of hydrogens. So there are 6 primary hydrogens to 2 secondary hydrogens, you should see this versus this as a 3 to 1, just on probability alone. However, what we actually see is a 1-to-1 ratio of these two species. A 1-to-1 ratio of these two species. That's because the two competing factors. While chlorination is faster and more reactive of the halogen, so it is a rather unselective process. So whatever it bumps into. But there is some favoritism. So if it was just speed, you would see the 3 to 1. But it is somewhat moderated by the strength of the primary versus secondary bond. So we get a 1 to 1. Now bromination, remember we said fluorination was too strong, too fast. And iodination is too slow. So moving down from fluorine to chlorine, bromine is slower and less reactive. This will be a trend we'll see often, is that bromination is the slower and more controllable reaction. So when we do bromine, it's less reactive, and so the bond strength factor dominates, and so we get a favoritism of just the secondary attack. So we just see 2-bromopropane. And only a minor product of 1-bromopropane instead of the 50-50. And this is due to if we look at the enthalpy of the hydrogen radical extraction, that the first step is always endothermic. Well, actually, sorry, I spoke wrong. The hydrogen extraction by bromine is an endothermic process, while chlorine is exothermic. So we have if I jump back to my diagram real quick. So we're saying okay, we have our propane and we have a chlorine. First step is going lower here, and then we have to form and HCl. And then we have the next step. While doing the same process with bromine, we have it really only forms that guy in HBr. The other one's going to be okay. Maybe the two species have different energy barriers, but either way, it's exothermic, and the extra energy is going to be constantly pumping energy into the system and help speed both reactions along. The endothermic process is going to make one of them favored. So why is halogenation useful? Well, we already kind of hit this, but let's remind ourselves. Halogens are good leaving groups. So once we've added a halogen, we can now nucleophilically substitute our species. We can undergo elimination to form double bonds on our species. They are very good leaving groups. We can replace them with hydroxide. We can replace them with amides. We can replace them with ethers. All sorts of things can be done to replace these leaving groups. Halogenation can be used to generate chiral mixtures when you have secondary and tertiary carbons. This is due to the radical intermediates is planar and can attack from the top or bottom lobe. So So you're going to get a mixture. So in this case, a further halogenation can create diastereomers. Now, you cannot favor one chiral center easily, or at all, I don't think. But there you go. I mean, so like, since you have, okay, say we have this particular isomer, which should be R, right there. R isomer. Well, you can create it. You can create an RS and an RR isomer because it's not going to selectively choose one versus the other. And then, of course, you can try to separate those out. Now, another issue we will talk about is allylic radicals. Allylic radicals are particularly stable. This is a thing we're going to see when we talk about conjugation in the next few chapters. Conjugation, where if we have a charge when we can move electrons around, we can flip double bonds around. In the same way, we can flip radicals around. The allylic radical is even more stable than a tertiary radical because we get the resonance delocalization. So the radical is delocalized between two carbons instead of just one and stabilized with a bunch of hydrogens. Now, because of this increased stability, a allylic carbon can be selectively brominated using a very mild halogenation agent. This guy, NBS. You can just remember NBS, but NBS stands for N-bromosuccinimide. That this generates just a small amount of bromine radical. We can very controllably and release bromine. It's a very mild. The milder the agent, the less it reacts with. So remember, chlorine reacts with just about everything. Bromine, it can favor secondary and tertiary over primary. NBS, we can react only with allylic positions or vinylic positions. The vinyl group is one where we have a double bond attached to something. So we can attack adjacent to the double bond. So NBR bond is weaker than the bromine-bromine bond. And it's very slow when it reacts, so it can generate only trace amounts of the bromine radical species. So we can try to minimize the reaction with other things. The bromine's only going to hit and react with the allylic radical. So if you add more NBS, if you concentrate the NBS, so we make the allylic radical in HBr, and then the NBS can then convert HBr into bromine. So the idea here is that while the bromine radical initially could react with a bunch of different species, it's so low that it's a slow process, and it allows the allylic radical to be favored. Because remember, there's all these different competing reactions that sometimes do nothing. Because we keep the bromine concentration low, we don't add across the double bond. So real quick, I want to draw these out real quick. So the idea here is we could generate these possible radicals. Oh, sorry. Let's see. Or maybe I'm not. Yeah, I'm trying to think. I'm trying to. Oh, sorry, these possible radicals. So we have this species. We can generate these possible radicals. But if this radical bumps into a weaker held hydrogen, if this radical bumps into a weaker held hydrogen on another of this species, it's going to favor this guy's a secondary, this was a allylic, this guy's a primary. If this guy bumps into another hydrogen from these species, if there's no more bromines to react with, it's going to bump, and eventually this guy is going to be favored because this guy is going to have the weakest, the most stable radical, less likely to bump into this and pull off a hydrogen. Now, so we have so little Br radicals that mainly this forms, and eventually we form some Br2, which can react to form Br here. But there's so little Br2 that we don't accidentally do this reaction. We don't want to accidentally go and add 2 Brs across the double bond. We don't want to accidentally do that. So we're not going to do that because there's not enough. This concentration is low. So that's not going to happen. But the other thing that the end of the slide says, because this is conjugated, because it's delocalized through here, you're also going to form this species. So you're going to get these two species. You're going to get those two species where it can, the double bond is going to delocalize in that region. So you get two unique bromination products. Now, the last type of reaction is radical additions across the pi bond. Halogenation across a double bond serves no purpose other than getting a mixture of diastereomers, as opposed to the racemic chiral products that we get in anti-addition. So the idea here is that when you do double bond bromine addition, it's always going to be anti. So you're going to get RS or SR. But if you want RR and RS, or SS and SR, bromine radical across the double bond will get you that. So you, because it's, remember, this is square planar in that bottom, in that radical form. So the bromine, the next halogen can add either from the top or the bottom. However, if you add HBr and use light, you can get a regioselective addition when compared to a normal electrophilic addition. So normally we could add HBr across a double bond, but now instead of it's all about how the order of addition. The order of addition. Normally, let's look at that. Let's look at that and think about that for a second. Normally, if we're doing electrophilic, remember we're doing that by charge. Electrophilic, if I have electrophilic. Remember, I just want to say this guy is greater, more stable than this guy. The same way as this guy is more stable than this guy. So, when we do HBr electrophilically, the double bond goes and attacks this, and we have the H is adding first. So we form carbocation and the bromine, and then the bromine attacks there. But when we split it with light, we create a Br radical, which is going to add here. Sorry, single arrow. Going to add here to form. Okay. Yeah. So we have R dot R Br, and then this guy will then single arrow pull off the H and thus propagate. So it's all about order of addition. What's attacking what? In electrophilic addition, the pi bond attacks the hydrogen. The negative pi bond attacks the hydrogen. And then the bromine adds. In our radical mechanism, the bromine attacks the pi bond, the bromo radical attacks the pi bond, and then the hydrogen adds. So we get the opposite addition because it's adding the functional groups the opposite order. So that's just something to think about. You adding HBr instead of Br2, you can get the opposite regioselectivity. Now, this radical mechanism is anti-Markovnikov. So it's anti-Markovnikov. As the electrophilic addition, it was Markovnikov. And this is all about the order of addition and the stability of the secondary radical. Yeah, it's basically what I just said. I jumped ahead on my slide. So why are we forming the radical bromine instead of radical hydride? Is because if we use a peroxy radical, the peroxy radical forms an alcohol. It steals the hydrogen, and so we preferentially form a bromo radical. And so that's why we can form it like this and add just there. And of course, if we get enough bromine radicals, it's going to just reform Br2 and stop. Please note, we cannot do this with HCl and we cannot do this with HI. We can only do this with HBr. The bond strength is not such that we can add in this way. Finally, lastly, polymerization. Polymerization is, well, not really lastly, but polymerization is a common thing we'll do with radical mechanisms. It allows us to make very long chain hydrocarbons. They will occur under the mechanistic steps of radical reactions. A small amount of initiator is used to activate an alkene. The alkene can then undergo propagation with other alkenes and increases the chain length. Eventually, a termination step occurs between other radical chains, and the chain length is controlled largely by kinetics and the ratio of initiator to alkene. So at a certain amount, it starts slowing down, especially as we run out of alkene, and so there's a chance it'll run into other things. But a lot of the polymers we know and use happen in this way. Like propene is used to make polypropylene, which we use in, like, for example, syringes. Tetrafluoroethylene can be used to make polytetrafluoroethylene, which is Teflon. We use in dental floss and other non-stick, non-reactive surfaces. Other examples of radical reactions are chlorofluorocarbons and their respect to the ozone. I'm currently talking about these with my environmental class. That the idea that halogenation is one of the common reasons for ozone layer depletion, the ozone hole that we are still repairing. That ozone normally absorbs ultraviolet light via the following reactions. That ozone absorbs the UV light, splits into O2 and O. And O, if a monooxygen bumps into an ozone, it can decompose the ozone. But this happens naturally. But this is a very slow process, largely because monooxygen concentrations is very, very low. And if a monooxygen bumps into an oxygen, it can reform the ozone. However, chlorofluorocarbons, which were very useful because they are typically very unreactive, non-toxic, non-flammable, multi-use gases and solvents. They are non-reactive under most conditions, but under high-intensity light, they will fragment off chlorine radicals. So they get released into the atmosphere, they don't react, they don't wash out, so they can get up to the stratosphere where the ultraviolet light concentration is high, and then we zap them apart with ultraviolet light into chlorine radicals. That chlorine radical can then react with ozone, form a chlorine monoxide radical, and that chlorine monoxide can reform a chlorine radical when it bumps into monooxygen. So this is one of many catalytic processes that were once responsible for a large ongoing ozone depletion event that started from the 1930s. However, we have largely reduced a lot of our CFCs and switched to other hydrofluorocarbons and other things that are less likely to impact the ozone layer. So it's still improving, but it's not expected to fix itself until the 2050s. And finally, last slide for this chapter. Another example, antioxidants. Antioxidants work by successfully capturing radical atoms or by forming stable radicals. Phenols are a common useful antioxidant, especially in wines and liquors or liqueurs. The idea that phenols, when they're there, when we get large amounts of oxygen in there, it can spoil the wine. But as long as we have enough phenol, it's going to then capture the oxygen and consume it and keep the wine good. The alcohol of the phenol is capable of losing a hydrogen to the radical extraction, but then it delocalizes the radical throughout resonance and thus prevent chain propagation. So vitamin E very capable of capturing this. BHT, this is one that is commonly added to a lot of our chemicals, highly reactive chemicals. We had just a trace amount of butylated hydroxytoluene. Notice these OHs on the rings. These OHs on the rings. That's the phenolic group. That even though we form an O radical, we delocalize that radical throughout the ring, and thus stabilize the radical in it so it doesn't react. But that is the rest of our chapter. That's the rest of our chapter. We will continue and look at the homework on Friday one way or another. I said if there is no class tomorrow because of school being canceled, we'll just have to push all the labs back a week. But if we do have class and you can make it to lab, try to make it to lab. If you are normally part of the Wednesday lab but you can make it to the Thursday lab, try to make it to lab. Either way, have a good day.